think this is about everybody, or as close to it as we're likely to get. Welcome back to school. Do you all have your trapper keepers and your pencils sharpened? I love school supplies, so you don't get that oomph in this level anymore. So I encourage enthusiasm however I can find it. For those of you who've not met me, I'm Lisa Hoffman. I am your instructor for this joint section of CLDP 948 and EPSY 906. I have to say that slowly because I know someone whose last name is Espy, and I'm forever getting it wrong because of that, so it's EPSY 906. I am the doctor. I have a tenured job and everything, but please just call me Lisa. No one calls me Dr. Hoffman who actually knows me. And hopefully by the end of the first week or two, we'll get to know those of you who I don't know already. I sent out an email last week. One of you got it bounced back. Who didn't get their email? Did anybody get their email? You're auditing. Okay. So then what you need to do is send me an email, please. So yes, any auditors, if you would like to be put on the distribution list for announcements, if you would like access to the online homework or the course readings, please send me an email with your name, your KU ID, and your Blackboard ID. That way I can find you and enter you into my database. So yes, please do that. If you spell my name correctly, you will get my email. I am lisa@ku.edu. L-E-S-A. That's left over from when I was a graduate student here. They let me have it back when I came back to work here, which I was so happy with. But so we have a website. This is where everything is going to be that you need in terms of course materials, with the exception of the readings. Since the readings are copyright protected in some form or another, those are inside Blackboard. So I combine the two sections into one class within Blackboard, and all of you should have access to that. I also made it publicly available, so those of you who want to add it yourselves can, or if you send me an email, I will do so. Otherwise, everything here is going to be electronic. If you're old school and you like to print out paper, go ahead, but it's got to be your own paper. The exception to that is if I am late posting handouts. If I don't have them up by like the day before, then I will bring paper for you. But the idea of being in this classroom is that you can take notes electronically, either on your own laptops or on the provided equipment here. Let's see, textbook. This is it. I have it here in case anyone wants to look at it. It has words and everything. So there's a whole lot of SEM textbooks out there. I picked this one because it focuses more on the measurement building portion of the progress. That's the part that's way trickier. And I like this author. He does a good job of writing in English. He has lots of examples. There's lots of syntax from different programs. So that's why I picked this. There's also a whole lot of articles that I am supplementing these readings with. You're not going to be tested on the readings. The idea is that I wanted to give you references to follow up on some of the ideas, or people who explain things a little bit differently than I do, as a point of comparison. And yes, it's really hot in here. I'm very sorry. We already went over that. Those of you who are sitting by the fan, feel free to adjust it as needed. The irony is that my office is on the other side of the hallway, and it's always freezing over there. So it's just we haven't gotten to equilibrium inside the building. Software for this class, we're using M+. That being said, pretty much everything up until about the second half of the course, you will likely get the same answers if you know how to use Levon and R or any other type of SEM package. M+ is both good and bad. Good, it's easy to use. The syntax is relatively simple. It does everything that we want it to be able to do and then some. So this is the problem in the SEM world. Certain packages only do certain things, and when you're trying to teach the intersection of modern approaches to measurement and structural equations, there's not very many choices. The downside of M+ is that it's expensive. I do not expect you to buy it. This room has M+. I spent part of my startup package to make sure that it does. And after class, I have office hours in this room from 2:30 to 4. And I also have a graduate teaching assistant. Say hi, Zhihong Zhang. Close enough? I'm going to work on it, but yes. He is the TA for this course. He took it last year. He is going to have office hours from 1 to 4 on Thursdays. So the idea is that even if you don't need help, this is your chance to access M+ on campus. It's also available in the Watson Computer Lab. This room, by the way, is not a computer lab. This is a classroom that is owned by the Speech Language Hearing Department, and they are nice enough to let us in when it's not being used. My hope is that, like we had in previous semesters, I will be able to grant each of you remote desktop access to this room so that you can log into these computers after hours. I haven't got that set up yet because I was waiting for the final set of auditors and the roster to get built, and I'm hopeful to have that set up within a week or two. So that's the skinny on that. If you do have M+, I will note that it never expires. So that's one of the nice things about it. You can't have updates unless you stay enrolled in their continual payment system. But once you've installed it, it never dies, unlike other programs such as SAS or SPSS. Let's see. Questions so far? Okay, so what are you going to be doing on your end? Showing up to class, that's number one. You'll notice that I have this lovely accessory here. It's not just a lovely accessory, a brooch if you will, but it's a wireless microphone. I am going to stream this class on YouTube. So I have a YouTube channel. It's actually uploading right now. So in theory, that means that you don't have to come. However, I am prone to doing things like running this out of batteries, forgetting to hit start, or otherwise interfering with my own recording process. So this is not an online class, it's not a flip class. I cannot guarantee that every lecture will be successfully recorded, but that is my intention. The idea is that rather than asking questions about what you don't understand, you can take a first pass at answering them yourself by reviewing whatever you need to. If you've reviewed the material and you still have questions, then of course, please feel free to email me or ask me, as well as the TA at any point. So that's what you'll be doing, reviewing videos as needed in addition to attendance. I have 7 out-of-class quizzes planned. Those are due as listed on the syllabus. That is prone to be moved by a day or two depending on how long it takes us to go certain things. But the idea is that these are quizzes that go over sort of the big picture of what I want you to have gained out of each topic. These are questions that you should be able to answer off the top of your head or very close to it. And if you can't, that's an indication that you've missed something big along the way and that you need to spend more time on that. So those quizzes are going to be due on 1 o'clock those days. That way we can go over them in class. You get points for doing them. I'm not going to grade them in the sense of marking off for being right or wrong. I'm going to read them. And if 10 out of 14 of you give me the same wrong answer, that's very instructive for me as to what I need to review or misconceptions that I need to clear up. So it's me checking in with you to make sure that the major points are getting through. That's the purpose. It's effort only. Homeworks, otherwise, in the last version of this class, I had 7. I couldn't make it fit with the syllabus this year, so there's going to be 6. Half of them are you do your own data analysis or writing, and half are going to be practice with canned data sets. So unlike if you've had me for multi-level, you didn't get a chance to analyze your own data because there's way too many variations of multi-level. In measurement models, I can actually tone it down into something that I think each of you can find data to use. So the idea is that you will try to analyze fit measurement models to data that are meaningful to you. I'll give you some of the more specifics later on, but the idea is that they should be scale responses of some kind. They can be performance items, they can be self-report, they can be rated items. 1, 2 constructs, maybe something very small. If you're sitting there and thinking, I have no idea what I would ever use for this assignment, come talk to me and I have lots and lots of data. So you will get a chance to practice with the models using canned data where you will get a chance to see whether or not what you're doing is right or wrong immediately, and then you'll get a chance to do it for my feedback. Anything that is written, those written assignments, you get to revise. So I will give comments in the text as well as suggested edits. If you address all the comments, you get all the points. It's just like in real life. In this profession, it is never the case that you are expected to get something right on the first try, right? How many of you have ever had a paper come back accepted on the first try? Yeah, me neither. It's not going to happen. How many of you had a grant funded on the first try? Me neither. It's not going to happen. So the idea that you can be responsive to feedback and make your product better is an important skill for you to practice, and I want you to be able to do that in here. I will show you, it'll be ready probably next week once I get all of the rosters built. The other assignments use an online homework system where there's 2 kinds of questions. I will ask you questions that have a very clear right or wrong answer in terms of a number, such as enter the parameter for this item for this model, and if you're right, it turns green, and if you're wrong, it turns red. So that way you know immediately if you are looking at the right set of output. I will then ask you questions about those models, and those questions are interpretation-based, and you'll get immediate feedback after you submit on those instead. So it is, in theory, possible for you to get all your points the first time through on those assignments. It's only the written stuff where we would need to have revisions. So there's going to be 3 of each of those. The first one, homework 1, is not due until the 3rd week of class. That one is going to be you giving me information about the data you want to analyze. So that one will be super easy. All you'll have to do is track down an article, read it, and answer some questions. So I will get that up probably by Wednesday so that we can look at that, and that will have the parameters as to what your items are going to be. Otherwise, important dates on the syllabus. I'm going to be at a conference, most likely, the week of the October 10th through the 13th, so there's no class that day. The Monday after is fall break. So that puts together a nice little week where if you need a break or you want to schedule a trip back home, there you go. Likewise, I have given up holding class on the Monday of Thanksgiving week. I've done it before and had like 2 people come. I'm like, I'm just not going to do it. So again, if you want to book a cheap plane ticket to go home for Thanksgiving, go for it. You can leave as early as, let's say, maybe the 14th or 15th. So I just wanted to point those out to you so that you can plan accordingly. We also miss class on Labor Day, which is, 2 weeks from now. And last but not least, finals week. There is no final in here. All your job is to turn in any outstanding work by the Wednesday of finals week. If you follow along with the syllabus that I have planned for you, you will have already turned in everything by the Friday before. So if you want to be, you can be done the last week of classes, and there's no final and there's no stress. Deal? All right. For those of you who have colleagues or lots of notes, just sit and listen, because we're going to hit all of this in much greater detail as the semester goes on. I just wanted to give you sort of the big picture of what the class is about. So if you don't think this is going to meet your needs, then you can decide to look elsewhere instead. So this is lecture 1. All right, so theory. In the world of measurement models, several types of models are referred to as theories for reasons that are still unclear to me, to be honest. But test theory or classical test theory or item response theory, these are terms that you will hear. And what they mean is just this basic idea that we are using models in a particular way. So measurement and statistics really are the same thing because measurement models are statistical models. They are a theory in as much as any model is a theory. So we don't say that we run like a regression theory analysis, right? But when you run a regression model, you're saying that you have a reason to think that X and Y are related. So it's not all that different than what you're typically used to thinking about in terms of statistics. And they are ways of operationalizing and solving problems that are inherent in measurement. So when you only know one way to do things, you are stuck to that as your only option. The classical sense of classical test theory, the idea that you can take items, add them together, and come up with some sort of score, that works fine for certain things, but it makes a whole lot of assumptions, and it starts to break down the moment that you have any kind of complexity in how the items are to be matched with the samples. And so these are ways to extend that idea into something that is designed to solve practical problems. So there's 3 branches of models that we're going to go over this semester, and the one that you know already, this is classical test theory. So as background for this, I was a graduate student at KU in psychology, and I took a course from Susan Embrenson on item response theory. Now, I don't know if you know who this person is, but she literally wrote the book. Like, she's like the queen of that little world, and I'm shedding paper, sorry. And it was her book in the course. And the first chapter of her book, you're going to read several chapters from it on your reading list, was all about contrasting classical test theory and item response theory. And I was reading it, and I'm like, I don't think I know what classical test theory is. Like, no one's ever called it that before. But all the things that you learned about measurement in introductory courses, that's classical test theory. It's the idea that you can add items up and have that total represent something meaningful. So the way that you know that it's meaningful, validity studies. Does that total correlate with the other stuff it's supposed to in the way that you think it does? Reliability. Do the items kind of hang together in a way that makes some sort of sense? And we will stop by this framework as a way of actually knocking it down. Because here's the truth, folks. Alpha sucks. You heard it here first. Cronbach alpha is useless. It is worse than useless because it's a tradition that needs to die. And I'm here to take it down. So a lot of the things that you will have learned about that are important in terms of establishing reliability are based on 1900 technology that is no longer necessary. It's as useful to you as a course on how to program a VCR. Once upon a time, it was something you needed to do, but it's just not anymore. So we will stop by this kind of stuff so that we have a point of comparison for how the modern measurement models actually function. So, by the way, PRI, this is my abbreviation for probably. I will say certain words like that I have to define in advance. So if you say PRI, that's what that means, just as an FYI. So what are we going to be doing? Building models that measure latent traits. Latent means unobserved. Trait is the idea that it's a continuum. So you have a construct in mind, such as these things. Intelligence is a classic example, measures of personality, depression, attitudes, achievements, nils, skills, knowledge, that kind of thing, where you understand your hypothesis is that people differ continuously from each other on this latent trait. But we don't know how to measure it directly, so we give multiple observed measures, and we hope that the commonality of those measures is then indicative of this latent trait. So it's the commonality that matters, and that means that what we're saying is that the trait came first. So these are models that are known as reflective models, meaning that I have this level of, let's say, extroversion, and that causes me to answer item 1, 2, 3, 4, 5 in a particular way. But extroversion came first, and extroversion would be there even if the scale didn't exist. Contrast that with a different kind of measurement model, which is not actually testable, which is formative, where the trait comes after. So a classic example of that is socioeconomic status. You have your level of education, your neighborhood, your income level, your parents' education, and that's just sort of like a big ball, and that's socioeconomic status. Another construct I can think of that might be relevant for you is, say, lack of free time. Think of all the things that might make someone busy. Classes, teaching, research, children, other family responsibilities, hobbies, pets, yes, thank you, community groups, training for a marathon, like all kinds of things, right? What else do we do? What am I missing? Oh, personal relationships, right? Like friends, loved ones, that kind of thing. So somebody who is really busy might be only really busy because of a few of those things. They're not necessarily correlated with each other. It's the whole is greater than the sum of the parts. That's what's known as a formative measurement model, and we are not doing those. They're not testable. There is no way based on just that data to say that you've measured something that is different than the individual pieces. So all of the traits that we're going to be measuring are reflective. The trait came first, and it causes the way you answer the questions, such that the correlation among the questions is the trait. We take that covariance, that correlation among the answers, we put a circle around it, and we give it a name. That's how these models work. So if your traits that you're interested in don't quite fit that, this may not be the kind of models that are going to work for you. So is that giving any of you concern or pause, questions?
The SES would be one of those forms of example. So I guess I still don't understand how the model type is sort of aware of those things. Like if it's a factor influencing an outcome, why does it matter?
It's the question is whether or not the indicators of the factor, so the measures that are being caused by the factor, whether or not the correlation among them can be used to support the existence of one or more traits. In formative models, the arrows go the other way. The idea is that the items cause the trait, and there's not necessarily a correlation among the items. So you really just have to believe. The only way that you can sort that out and actually have the model be identified, like able to be estimated, is if that SES thing goes and predicts this other stuff. And it's the relationship between the items and that other stuff that helps provide enough information for the model to work. So if you have somebody who, like, their education might be correlated with where they live, it might be correlated with how much money they make, or it might not, right? Who are the best paid people in our society? Is it PhDs? I don't think so. It's professional athletes who may or may not have finished college, right? So at an extreme level, these things are not necessarily related. Within a given sample, they might be. But if you can say, if you're not expecting a correlation, then it's probably not a reasonable thing to think of it as a factor model in the way that we're going to think of it. So it's almost more of a theoretical distinction than a statistical one. You have to believe that it goes one way or the other. So, Emily?
If there's some part of income, for example, that isn't explained by the trait, the trait isn't explaining all of the income, then can you look to see how whatever's left in income is related to something else?
Yes. Yeah, so that idea of common versus specific, if you have relationships of your measures with other stuff that aren't the same, that's another indication that maybe you don't have a trait. Because in theory, there shouldn't be those extra relationships. The trait should handle them all. It should represent them all. All of these, by the way, are empirical questions. They're answerable with data. It's just this big distinction of formative versus reflective is more of a theoretical one. And it's the difference between, in old school sense, principal components versus exploratory factor analysis. It's that same distinction, whether the outcome is the measure or the trait. It's the measure in what we're going to do. It's the trait in formative or principal components. So beyond that, though, once we accept that we're measuring a trait that came first and it causes the way the data fell out, answers to questions or ratings, whatever you have, then there's a lot more commonality. So all of these models came about from different traditions in different fields, and so there's differences in terminology that boil down to semantic distinctions. So in classical test theory, the trait that you're measuring is called the true score. There's a classic equation, true score over total, right? True score meaning the good part, total meaning good plus bad, total good plus error. In confirmatory factor analysis, note that sometimes this is actually called confirmatory factor theory by some authors in corresponding from this other tradition where everything's a theory. The trait that you're measuring is the factor, or the factor score, or the latent variable, or the latent construct. All of those words mean the same thing. In my notation, by the way, I never make Greek symbols that I can't draw reliably on the board. So oftentimes, like in your textbook, the factor score is going to be squiggle 1. I don't remember what the name of it is, but there's squiggle 1 and squiggle 2. There's 2 Greek letters that I can't draw. Mine's F, because F stands for factor. In item factor analysis, that is confirmatory factor analysis for items that are not normally distributed. It's still going to be F because the equation is going to look pretty much the same. Those same models developed in a different tradition with a whole different set of notation, and there the factor is called theta. And theta is used universally in the world of IRT models, and so that's why I'm sticking with it, plus I can draw it semi-reliably. So to recap, true score, factor score, theta, latent variable, latent trait, latent construct, all those things mean the same thing. It's the thing we think exists that we're trying to measure with observed variables. The differences between these is in how the measurement process works. In classical test theory, the unit of analysis has to be the whole test, because what you do is sum the items to create a score. That score doesn't know how it was created. That means that if you want to have comparable measurement, you have to give the exact same set of items all the time. That's problematic for a number of reasons. It also makes untested assumptions. More specifically, using the score from the sum means that all of the items are unidimensional. They measure one thing and one thing only, and they do so equally well. Those are testable assumptions. I will show you how to test them. It's known as tau equivalence or true score equivalence, those ideas. Unidimensionality is the first one, though, because if you don't have that, game over. So all of the other measurement models are going to work with the items instead of the total, and that's the big switch. Each item is going to have its characteristics as part of the model, as well as the characteristics of the person answering the items, the respondent, their latent trait score. So the latent trait is a separate entity from the sum, and that brings about all kinds of advantages. You can test whether or not your items measure one thing or two things. You can test whether or not they do so equally well. And, more importantly, you don't have to give the exact same items to everybody. Given a pre-calibration onto the same trait, you can deliberately pick certain items that are going to be more or less sensitive. So, for instance, if you're doing longitudinal assessment, you don't want to give kindergarten students 6th grade math items, and you don't want to give 6th graders kindergarten math items, but you do want to measure math across elementary school. Well, how do you do it? You grow the test. You get a giant pool of items that are pre-calibrated onto a trait or two, and then you slowly work in the harder and harder items and drop the easier ones. That's known as vertical equating. That's a really big deal in the world of educational measurement. But those same techniques can be used in behavioral data to measure traits that are thought to develop along with the people who are developing. It also can be used to solve problems that exist because of multiple test forms. So I have a paper that will probably end up on the reading list at some point with the PPVT, Picture P-Body Vocabulary Test, that thing. It's had like 17 versions in its history, and the reason is because it's vocabulary words. And so they want to make sure that the words remain current, that they have the same properties, because certain words maybe become more or less relevant for certain generations. But if you give a different test across time, you can't measure change. So you can if you try to do it within a latent trait model. And so all of these frameworks, no matter what the type of model is, have that benefit, that it separates the items from the people answering them, and then it makes it so that you can have comparable measurement even without the same items, and you can test that you actually are measuring what you think you are. All right, so words. We'll start with, in terms of these latent variable measurement models, confirmatory factor models. Those are latent trait models for outcomes that are supposed to be continuous. And I mean continuous. However, most of the time they get used on what are known as Likert scale data. And it's a dude's name. It's not Likert, it's Likert. It's the idea that you have ordinal, like strongly agree to neutral, to disagree to that, those kinds of things, or sometimes, rarely, a little bit, always, like those kinds of scales. Those are not continuous. You can put numbers on them, but there's no way of saying, well, that the difference between sometimes and rarely is the same as the difference between sometimes and often, right? I can call that 1, 2, or 3, or I can call it 1, 17, and 3 million. It doesn't matter. All I know is that they're probably in the right order, but the relative distances are arbitrary. So those kind of data are more accurately analyzed with another type of measurement model, which is often taught in a whole separate class. This is the world of item factor analysis and item response theory. I put it together because these are literally the same idea, just for different kinds of data. So linear regression is to logistic regression, as confirmatory factor analysis is to item response theory. The only difference is that the predictor is latent. In regression, you have a predictor. It's sitting in your data set. In confirmatory factor analysis, it's latent. You just have to believe it's there. The correlation among the outcomes is what creates it. So you can have other kinds of measurement models for other kinds of outcomes too. They just don't have a name. So as an example, I'll probably give you this example later in class. I worked with a student at Nebraska who was measuring risk-taking behavior in adolescents, and they have this task called a stoplight task. Has anybody heard of this? No? Okay, I'm the expert. I'm a developmental psychologist today. So there's this task, and the kids are told that they have to get to a party as fast as they can, and they encounter a series of intersections. And if they hit a yellow light, they can either decide to go through the intersection and crash sometimes, or they make it safely a little bit faster, or they can decide to stop. And then they have a delay that's known, and it's a little bit longer than if they had made it through without crashing. So it's this sort of risk-reward proposition. So the outcome from this task is usually mean latency to brake, which begs the question, what if they don't brake? What if they zoom on through? There's no latency, right? And he said, well, they treat that as missing data. No, that's the definition of informative missing data, folks, right? The fact that they decided to go is indicative of the trait of impulsivity or risk-taking or whatever you want to call it today. So I helped him fit in his master's thesis, which was the done kind and is actually the published kind, what is known as a two-part model. So these are models that are typically used for zero inflated responses, like counts, but they can be adapted for continuous measures. So we had each item carved up into two dependent measures. One is a binary, did they go through the light or not? And we had a latent factor for one's propensity to either brake or not. And then, given that they braked, how long did it take them to decide to do that? And there was a separate latent trait for that. And it turned out in his thesis, the propensity to brake was the thing that actually predicted his further outcomes. It wasn't the one that people typically use. And I struggled with what to call that because there's not a name for it. But if you can analyze any kind of outcome with a linear model, you can do the same thing with a latent variable measurement model. So I would call that maybe generalized structural equation modeling, something like that. So if you're giving job talks, by the way, Lucas, if you get job talks or whatever, and you need to come up with words that make you sound as knowledgeable and statistically savvy as possible, let me know. I will give you the words. This is generalized latent variable modeling in the tradition of Schrondel and Rabahesketh. I can stick a few other words in there, too, if it makes you feel better. So once we have this trait built, once we have this circle with a name in it, indicated by whatever kind of information that we have, yes or no things, Likert scale things, latencies, any of that kind of stuff, then structural equation modeling is regression among those traits. You can have them be correlated, you can have them predict each other, you can do whatever you would typically do in a regression type framework. The idea is that you're doing it better because ostensibly the relations are specified amongst the good parts of the measures. The commonality is supposed to be more robust than any one of them would have been separately. So that's the world of structural equation modeling. When some of the items are not normal to whatever degree, binary, Likert, two-part, then sometimes the word generalized structural equation modeling gets thrown in there. So that's where we're going to end up, but we're not going to get there till the end of the semester because I got to be honest, it's going to be really anticlimactic once we do because the hard part of SEM is getting the measurement models right. Once you get those right, putting arrows between the circles is trivially not more difficult. So if you go through the steps to make sure that the measurement model is right, which is what the textbook focuses on predominantly, then the structural model part takes care of itself. As an aside, other words that show up in this context, path analysis. I'm going to give you a real quick example of it, but I don't think path analysis is relevant here. Path analysis is just regression among observed variables. So you can do that in M+, or you can do that sequentially in any sort of regression package. Mediation, to me, is just regression with a better marketing campaign. I'm not one of those people that really likes mediation. Emily's like, how dare you?
No, I'm more like
Yeah.
in a good way.
So I mean, mediation is all about what is the relationship between X and Y after controlling for this other stuff. Doesn't that sound like regression to you? But then we add in fancy terms like indirect effects and blah, blah, blah. I will show you how to do this. It's just like 2 more lines of code for the models we're going to be fitting. So you will get this in here. Moderation, by the way, also marketing campaign, those are just interaction terms. You can do moderation in the context of latent variable modeling, but it becomes a lot trickier if the things that are interacting are latent variables. So I have this circle of what I think is something because I have commonality, and this other circle that I think is something because I have commonality, and then you're trying to come up with a higher level of abstraction of their interaction. That is computationally challenging to do, but it's not impossible. And what you would do to talk about the patterns would be the same as if they were observed variables as well. So, how's that? That's what we're going to do. We're going to end up at SEM, but it's going to take us a while to get there. This course is going to be different than other types of SEM courses because of the lineage of different kinds of models. I want you to understand that when you fit a measurement model, you get to figure out, based on the item type, what the right variant of it is, but otherwise it's the same idea. It's the same idea. The factor is the predictor. The outcome model is dictated by its format. All right. Questions before we keep going? All right. So a little bit of history here. I have a couple chapters I'd recommend if you're interested in more of the history, but I wanted to just briefly talk about why there's all these different words and people and terminology for the same thing. It's because different people developed these models for different purposes, and it wasn't until later that people started talking to each other enough to figure out the points of overlap. The other piece of it is that the mathematical developments of a lot of this stuff happened before computers made it possible. So the things that people were taught in graduate school in, say, the 50s and 60s and even 70s were out of necessity, because they didn't have, they couldn't run maximum likelihood on their smartphone like you can nowadays. And so it's unfortunate that some of this stuff is still very common when it doesn't need to be. Nowadays, through computing, we can do things a lot faster and more efficiently that would have been impossible several decades ago. And so what's funny about this is that I call this sort of modern psychometric methods. The models that you're going to learn about were invented in the 40s and 50s. They're old. It's the software that's modern. It's the ability to actually put it into practice. So, 1904. That's the common roots of what we're going to be doing here. 2 papers from Charles Spearman. So he has published a whole lot of stuff. One of them was designed to come up with measures of reliability for use in classical test theory. Those are still used today, alpha being one of them. And the other is the idea that you can have commonality across measures be indicative of a trait. And this is the idea of common factor theory, or CFA. So classical test theory then, a picture for classical test theory would be used like this. So in these pictures, you're going to see lots of them this semester. Things in boxes are real. Things in circles are pretend. So in my data set, I may have a total score across items. That's the piece of information here. And the task then is to try and figure out, of this single piece of information, how much of it is true versus error. So has anyone in here taken any SEM before? A couple people? Yeah, so does that model look solvable to you in an SEM context? Can you pull out 2 different things out of one thing? This is not identified. So not identified means not solvable mathematically. That's why I have question marks here. To be able to get some kind of indication as to what proportion of its total variability is true versus error, you have to make a whole lot of simplifying assumptions. Those assumptions are testable. And when you're taught classical test theory, you are never taught how to test them, because this framework does not have a means with which to do so. So we will stop by this as a point of comparison for how we will think about reliability within a latent trait context in which everything can and should be testable. Because the total score is what you take with you out of the analysis, the total score is your best version of the trait, it assumes that all items are exchangeable. And the way you make a better measure is to get more items. But more items, what kind? Just more. More is better. That's the idea. And this total score limits you to having to give the exact same items under the same circumstances in order to compare different people and different populations, and that is a big problem. So classical test theory then is focused on delineating how much of the variance is true versus error based on simplifying assumptions. Later variants of this are known as generalizability theory, which is taking error and carving it up into different sources. To me, by the way, this is a cross-random effects multi-level model, and I'd be happy to show you how to do that if any of you care about generalizability theory. In terms of where this lineage of classical test theory came from, in 1945, that's where coefficient alpha actually was invented by Gutmann, and then it didn't catch on until Cronbach talked about it. And so to the entire world, it's Cronbach's alpha, but apparently it's actually Gutmann's Cronbach alpha, according to Rod McDonald. So he has a couple chapters in your reading list as well. So just as an aside, they were fighting over this back in the 1940s and 50s. A classic textbook on classical test theory came out in 1950, and there's other textbooks that have came out since then. So we'll get into more of what these simplifying assumptions are in future classes, but that's the idea. On to then measurement models, CFA. Confirmatory factor model is a linear regression model. The difference is that the trait is the predictor and the trait is not observed. And this is contrasted with exploratory factor analysis. I have one lecture on EFA that I'll give you next week, and I will make fun of it the whole time. EFA is bullshit. It can never be used for anything that is answerable. Do you know why? Because there is no way to test the model. I can say, well, I think I have 3 factors in a Promax rotation. And you're like, no, I have 4 and it's Varimax. We're both right. We're both right, and that's the problem. And there are lots of papers that say things like this, that they found a different factor structure, except that it's exploratory and there's no answer. So we're not doing that. I will teach you just enough about it to make fun of it, and for you to be able to answer anyone who says, oh, you have to do an EFA first before your CFA. No, you don't. Confirmatory factor analysis, all that means is that you have a clue. You don't have to have a theory, and the theory doesn't have to be right. You have to have a clue to start with. Because once you fit a model and it doesn't fit, it's wrong, the results tell you where to go from there. So it is exploratory in the sense that it will likely be iterative, and you will likely have to refine your thinking, and you should probably test it on another sample. But the key difference is that we do so in a confirmatory way, where anybody looking at the same output could come to the same conclusion. There are significance tests. There are effect sizes. There are things that we can all agree mean good, bad, or somewhere in between. So here's what the model looks like. And you'll see this again. Don't worry about keeping track of all this. But I just want to make the point. This one over here, linear regression. An outcome for each I item, for each S subject, is a function of the intercept and the effect of a predictor, that's the slope. And to the extent that your predictor does not exactly match your outcome, there's error left over. CFA is the exact same thing with a whole different set of letters. Mu is the intercept, lambda is the loading, which is a slope, but it's still a slope, and it's multiplying the latent variable, the f. So all of the things that you learned about how to interpret an intercept and a slope are going to hold. We're going to fit this model simultaneously across all of the items that are thought to measure a trait, where f stays the same and the other terms switch out for the different items. So to the extent that this model fits, meaning that it predicts the same pattern of correlation that exists in the real data, that's what fit means. Fit means match. To the extent that the model matches the correlation pattern in the data, you can say there's evidence for the hypothesized dimensionality. 1 trait, 2 traits, 3 traits, however many you think you have. Critically, though, it's a linear model. This model predicts that the predicted outcome goes on forever and ever as your factor goes up or down, right? But what happens if you have, say, a 5-point scale? What's the highest possible response you can have? Not a trick. 5. What happens if you are the smartest person in the history of the world? What's the highest answer you're going to be able to give? 5. What if you're the dumbest person in the history of the world? What's the lowest you can get? 1. So this idea of a continuous slope that keeps going and going and going, we have to find a way to sort of like squish it and make it shut off. It needs, I'm like walking like an Egyptian here. Let me do the 5 and the 1. So the idea that we take a line and make it bendy for responses that are bounded, that is item response theory. So factor analysis came out of work trying to find out how many factors there were for intelligence and personality. It got developed further by introducing software with which to do these things, Literal, which still exists today, although I think it's pretty much died amongst regular practitioners. But then this idea of IRT came out of the need to create bounded responses. And so it's borrowing actually some concepts from psychophysics about how you can have, what's it called, stimulus detection, where there's some point at which your perception of stimulus switches. And they borrowed the functions that they found in that to fit to these sorts of models. So IRT, item response theory, is latent variable models for non-normal outcomes. Well, that's pretty much all the data that you guys are going to have, is my guess, is going to fall into this framework. So in your assignments, you'll get a chance to do CFA first, and then you'll get a chance to contrast what happens when you fit it the right way with these sorts of models that appreciate that you can only have a 5 or a 1, for instance. So you end up with these pictures like this, where the x-axis is theta. What's theta again? Do you remember? This is the audience participation portion. What's theta?
Like the factor score for IRT.
Yeah, it's the factor score, the truth score, the latent variable, the latent construct, the latent trait, whatever you want to call it. That's the x-axis. The y-axis is probability. So this is what it would look like if you had, say, a binary item of yes, no, or correct, incorrect. The best you can do is a 1, and the worst you can do is a 0. And so the model, rather than predicting a linear relationship between the trait and the predicted outcome, it predicts a bendy one. So these predictions are what's known as item characteristic curves, or ICCs, not to be confused with ICC from my other class, which is intraclass correlation. And these lines differ from each other in up to 4 ways. The 2 that are almost always talked about in this context is, one is a location, sort of where it starts to rise, where it hits 50-50. Another is the steepness of the line. Steeper is better. It means it's more related to the trait. The other 2 are more common in educational settings, upper and lower asymptotes. So for instance, if this item has distractors that are not very good, and so people have a greater than, say, 25% chance of picking 1 out of 4 correctly, it would have an asymptote at the bottom here that should be elevated. And likewise, if one of the items is unlikely to be perfectly reliable, if there's sort of a mess-up factor that should show up, then you end up with something that asymptotes below 1. But the point is, it's the same idea. You are seeing how well your trait predicts your item, but you're telling the model that the predictions have to be bounded within the range of the response format. And so for anything that is a Likert scale type of item, so 0, 1 up to 5 to 7 categories, there's a debate about how many you need, where you can be normal enough. Those types of responses are best analyzed here. The catch is that the model itself looks way different. IRT models look nothing like regression models, and that makes them hard to explain. But it turns out that you can algebraically rearrange it into something that looks exactly like factor analysis. And when you write about it that way and you talk about it that way, then the same model is known as item factor analysis instead of item response theory. So I will get you used to both versions of these models, because depending on who you're writing for, one may be more useful than the other. Those of you in the College of Ed, you're going to learn IRT. Those of you from psych or sociology, you're going to learn item factor analysis. You're all going to learn everything, but in terms of the words that you put in your talk, talking to different audiences, and the versions of the parameters that you give them, that's what it is. And so then there were two different lines of thought that developed this. There's Lord and Novick, classic research by them. A separate line of development by someone called Roche. You heard of Roche models before? Those are IRT models that don't have different slopes, but don't ever let a Roche person hear you say that or they will hurt you. Roche people say, no, we are not IRT models. And I'm like, you kind of are, dude. But that's a whole separate thing we'll get to later. So that's the big picture. Why should you come back? Here are the benefits of working within this framework, a non-exhaustive list. Explicit testable dimensionality. If there's a debate in your field about whether something is really one thing or two things, I'll show you how to answer that question, or two things or three things. The idea of measurement reliability, that is specific to the level of the trait. How do you know for whom your trait is going to be well measured? It turns out that reliability isn't just a single number, and it shouldn't be thought of that way. You can give comparable scores even if you change your items in this framework. That's the big one. You can examine the extent to which an instrument works the same way across different types of people. So this is the idea of measurement invariance or measurement equivalence. When it's said in a CFA framework, it's called differential item functioning in an IRT framework. But it's a big deal whenever you want to give a test on a sample for whom it was not intended. You have to demonstrate that it works the same way. Different ways of looking at validity, and besides the typical ways, there's internal evidence. I don't think we'll get a chance to talk about that too much. And you can have different response formats for your items, and so that's actually a good thing in this world. Why is it problematic? Sample size. I know some of you work in special populations where you might have like 30 people. This is going to be mostly a theoretical discussion for you because 30 people is not enough to do a whole lot with. To fit these models and to have confidence in their results, casts of hundreds and preferably thousands are needed for what are known as calibration samples. They're harder. Everybody can add items up and create a sum score. Not everybody can do this. So it is harder than the traditional approach. It can be hard to wade through some of the readings. I try to pick things that are as readable as possible. And there's also people who are overly optimistic about what these models can do. I'm here to tell you, if you have a crappy item, SEM is not going to help you. It's going to tell you that it's crappy more definitively, but it's not going to make it any better. And even though these models are referred to as causal models, they're not causal. Causality comes from design. You still are having basically correlational patterns that you are specifying in your model, but you cannot say that you are causing anything just by putting arrows in. That's a big misconception about what these models can do. So, just some stuff to keep in mind. All right, so that's the intermediate summary then. This is what this class is about. If it's not going to work for you, I'm not offended if you don't come back, but I hope that you will, and I hope that you bring your friends, because we're going to have fun. So, any questions? All right, then office hours start now. By the way, if you come to office hours and I'm not here, it's because no one stuck around and I'm across the hall in my office in 3042. So, all right, I will see you on Wednesday.